Good day everyone. So today I am going to talk about hemodynamics. I am Arik Delacruz. I am an assistant professor too at the WVSU College of Medicine. So disclaimer, this lecture involves a lot of mathematical equations and just feel free to pause the video if you wanted to grasp it a little more. And another disclaimer is all of the pictures and images in this video is not mine. I got it from the books and also from internet sources. And this meme is from the internet. So the major reference for this lecture is from Guyton, textbook of physiology, and it is our textbook. Function of the circulation. The circulation serves the needs of the body tissues. The rate of blood flow is controlled mainly in response for the needs of the nutrients. In the heart, the rate of blood flow is mainly measured through its cardiac output and also mainly from the arterial pressure by the blood vessels. The heart has two pumps, the left and the right ventricle, connected in a series. So if you take a look at this diagram, so in this figure, we'll see here this is the heart. It is divided into the right side and the left side. So the right side will pump blood into the lungs to get some oxygen and carry that oxygenated blood back to the left side of the heart. Then the left side of the heart will pump oxygenated blood to the rest of the body to oxygenate them, and the oxygenated blood will return back to the heart. So this is the circulation. Note that since both hearts are pumping at the same time, cardiac output is the same in the pulmonary circuit and the systemic circuit. So cardiac output is the output of either the left or the right ventricle. Structure function of the systemic circuit. So the systemic circuit has organizations. So if you can see in this diagram, the systemic circuit starts with the aorta, then branches out into arteries and into arterioles and into the capillaries, where there will be exchange with the tissues, and blood will exit through venules, then bigger veins, then going back to the vena cava. So to elaborate further, arteries transport blood under high pressure because it is coming from the left side of the heart. Since it is under high pressure, this is sometimes called the stressed volume. Volume with pressure is stressed volume. Arterioles are sometimes called control conduits because these vessels are regulated by its smooth muscles and mainly influenced by the autonomic nervous system. And the arterioles has the site of highest resistance in the cardiovascular system. Capillaries, again, are the site or the vessels which facilitate exchange with the interstitial fluid. It is mainly done through its capillary pores, and since the capillaries are the most numerous in this circuit, when you combine them all, it possesses the largest cross-sectional area and surface area. Compared to arterioles, arteries, veins, venules combined, no. So this has the largest cross-sectional area if you combine them all, of course. Venules collect blood from the capillaries, and veins transport this blood back to the heart. Since the veins doesn't have much pressure because it is way farther from the heart, it is of low pressure and thus it has unstressed volume. But veins contain the highest proportion of the blood in the body, as we will see later, and they are sometimes called the major reservoir of blood. So in this slide, we will see the proportion of blood present at any time in the circulation. So in this image, you will see that veins contain the most blood at 64%, roughly around 2/3, and the rest are shared by arteries, arterioles, systemic capillaries, heart, and the pulmonary vessels. So it is again seen in this figure on the right side. Now, if you have to draw a line over here, which the first figure is that pulmonary circulation, only 9% of blood is found. In the heart, around 7%. But in the systemic circulation, it's around 84%. So majority of the blood is in the systemic circulation. However, much of the blood in the systemic circulation are seen in the veins, venules, and venous sinuses. This is around 64%. Arteries and arterioles around only 20%. We go now to the cross-sectional areas of each vessel. In this, here we can see that the aorta has around 2.5 centimeters squared. When you combine all arteries, it's 20. Arterioles, when you combine all of them, it's 40. Capillaries, which are the most numerous in the systemic circulation, has 2,500 centimeters squared. That's a lot when you combine them all. It is bigger than the aorta. Of course, they are distributed very well. Venules is around 250. Small veins, it's 80. And vena cava, it's 8. So from this table alone, we'll see that the vena cava is larger than the aorta. But the largest, when you combine them all, are the capillaries. So this is again the diagram showing the artery and the vein. Then this line over here, the total area. The area occupied with the capillaries are the highest one. Pressures in various parts of the circulation. At this point, we'll know that the closer it is to the heart, as the heart is pumping, it exudes force. And force will translate into pressure on the vessel. So in this diagram, we'll see the highest force is from the left ventricle. Compare that to left atrium, where only minimal force is seen when it dumps into the left ventricle. So the left ventricle will have the highest pressures, followed by the aorta, of course, because it's the first blood vessel from the left ventricle. Then large arteries, then it goes down as it goes into the smaller arteries, arterioles, capillaries, veins, and goes back to the right atrium. And from the right atrium, it dumps into the right ventricle. So the right ventricle has some pressure in it because it is found in the heart, but the pressure is much less than the left ventricle. Then this right ventricle will pump it into the pulmonary arteries. Again, some pressure proportional to the pressure in the right ventricle. Then into the pulmonary arterioles, capillaries, venules, and pulmonary veins. And the cycle again goes back. From this figure, we will see that this one has the highest pressures from the left, and the right has some pressure but a little lower than the right. So let's take a look at the pressure in the capillaries. It's around 17 millimeter mercury, so around 17, around here. And pressures in the capillaries of the pulmonary circulation is around 7. Again, systemic circulation has higher pressures than the pulmonary circulation. So let's talk about the basic principles of circulatory function. Okay, we have 3 tenets. First is blood flow to most tissues is controlled according to the tissue need. Second is cardiac output is the sum of all local tissue flows. And the third is arterial pressure regulation is generally independent of blood flow and cardiac output. So the terms to remember here are blood flow, cardiac output, arterial pressure. So let's go back to this slide again. Here we see the pressure in the aorta and pressure in the vein. So the pressure in the aorta is around 120 and in the veins is around 15, 17. There is a gradual decrease of pressure. So there must be resistance from here to here because resistance will dampen the pressure in a vessel. What happens here and here is what we call the total body resistance. Let's talk about pressure, flow, and resistance. So this figure, this is a vessel. We will measure the pressure in the inlet and the outlet. Okay, in and out. Now, when a fluid flows through a vessel, there will be some kind of a pressure difference because of resistance. So as the fluid goes from here to here, it takes some resistance, and thus pressure in the in and the out should be different. So the difference of the pressure in the inlet and the outlet divided by the resistance that it encounters is what we call the blood flow. So Q is the blood flow. This is pressure 1 and pressure 2 divided by the resistance. So this is what we call the
Poiseuille. Jean-Léonard Marie Poiseuille.
So this is what we call the Poiseuille equation. I hope I got that right. It's Poiseuille.
Poiseuille.
It's Poiseuille equation. This equation gives us the relationship between pressure, blood flow, and resistance. This equation parallels that of the Ohm's law in electronics, but this is applied in fluids. So this is the change of pressure. It can be applied to any single vessel, organ, or the entire circuit. Let's talk first about Q, or the blood flow. Again, I'll put the equation right here. So the blood flow is the amount of blood pumped into the aorta by the heart each minute. So blood flow will be equal to stroke volume times the heart rate. Therefore, blood flow will be equal to stroke volume times the heart rate. So normal values, blood flow is around 5 liters per minute. Stroke volume is around 60 to 120 milliliters per beat. Heart rate is around 60 to 100 beats per minute. Next, we'll talk about resistance. So resistance is the impediment of blood flow through the vessel. So if we have to shift Q and the R, like here and here, we'll see that resistance will be equal to change of pressure over the flow. Again, we just transferred the Q and the R, and we have again this image. So the pressure gradient will drive blood flow. If we increase our resistance, there will be less blood flow. So if we increase resistance here, flow will decrease. Since there will be resistance, there will be a surge of pressure over here and less surge of pressure over here. However, if we decrease resistance, our pressure gradient will also decrease, but the blood flow increase. So more blood flow, decrease upstream pressure, and increase downstream pressure. Okay, feel free to pause and analyze. So we'll go back again to the pressure graph, but this time it is simpler. So the green bar over here, the zigzag one, represents the inlet and outlet pressures in every segment of the circulation, and we can see that it is in a decreasing trend from the aorta down to the arterioles. So what made this decrease? It's because of the presence of the resistance, that the resistance has also a decreasing trend along with the pressure gradient. So the pressure dissipates as the blood flows down to the circulatory tree because of resistance. There is a small drop in the major arteries, but a big drop in the arterioles. See? Only a small drop, but there's a really big slope over here. And again, because the slope flattens again, there's a small drop of resistance. Therefore, this segment of the arterioles represents the main resistant site of the circulation. This is usually called the total peripheral resistance or the systemic vascular resistance. And sometimes they call it the afterload. Now let's talk more about resistance and what comprises it. So this is the basic equation for resistance, and resistance is determined by the following parameters. So resistance is directly proportional to the viscosity of the fluid, the length, but it is inversely proportional to the radius of the vessel raised to the fourth power. So to summarize, resistance of the vessel is determined by vessel radius, viscosity, and length. Let's talk first about vessel radius. And vessel radius is the most important factor in determining resistance. For example, 1 mm radius versus a 2 mm radius. But if you raise it to the fourth power, 1 raised to the fourth power is 1. 2 raised to the fourth power is 16. So going back to this equation, resistance is inversely proportional to the radius. Therefore, a vessel with 1 mm radius will have more resistance than a vessel with 2 mm radius because it is inversely proportional. So if we take a look at the following image, so vessel 1 has, let's say, 1 mm radius and vessel 2 is 2 mm radius. This has a higher resistance than this one. Therefore, vessel 1 will have less flow than the vessel 2. On the corollary, vessel 2 will have 16 times more flow than vessel 1. We'll apply this to arteries being occluded. Here we have 4 arteries and their corresponding occlusion in percentage. This one has no occlusion. The second one has 20% occlusion. Third one has 50% occlusion. And the fourth one has 80% occlusion. So blood flow here, if we compare it to the other 3, here we have 100 cubic centimeters per minute. And this flow rate is cut to more than half with only 20% of occlusion. But if we have a 50% occlusion, we will have a flow rate of only 6.3. Far cry from the 100 flow rate. So only a 19% decrease or around 20, you will have half of the flow rate. And this is very important if we are talking about occlusion in the heart. A 20% occlusion in the arteries of the heart will actually decrease the flow rate to half. Now we can apply this to first coronary arteries of the heart. When it's 20% blocked, you will only have half of the flow rate to your heart and puts your heart tissues into danger. Second is this values over here represents pressure needed to restore normal flow rate to 100. Let's say 20% occlusion. You will have to double your pressure in order to maintain the same flow rate. This is very applicable to those with high blood pressures, especially if they have occlusion in their arteries. So probably a little less than 20% of occlusion, you will increase your blood pressure. Let's talk about viscosity. So viscosity is the property of fluid that is a measure of the fluid's internal resistance to flow. So every fluid has its own viscosity property. Every fluid will have a certain innate resistance to flow. In the blood, the prime determinant of viscosity is the hematocrit. If you can see in this figure, the higher the hematocrit, the more viscous the blood is. So normal blood is around 40% hematocrit. If we have to put more RBCs in our blood, then our viscosity increases. And if you don't have much RBCs in your blood, then hematocrit decreases as well as viscosity decreases. Viscosity will always be directly proportional to the resistance. So there are disease entities which increase the viscosity of our blood. It is increased in polycythemia vera. Thus, there will be increased resistance in our circulation. and decrease in anemia. So there will be decrease in resistance in our circulation. So this slide will show our normal hematocrit, mainly of the RBCs. If your RBCs will decrease, it will be less viscous. And if your RBCs will increase, it will be more viscous. So in order to get a grasp of this viscosity, I am showing you here the different viscosities of common fluids. Water, low viscosity. Olive oil has a high viscosity. And honey has the highest viscosity. Let's talk about length. So the greater the length, the greater the resistance. Of course, the more the fluid flows through a vessel, the more resistance it encounters. But in the body, vessel length is constant. It doesn't elongate when we grow up. It just stays the same. It doesn't shorten. It has been estimated that if you put all the blood vessels in the body end to end, it would reach 100,000 kilometers. Anyway, since the vessel length is constant in the body, it doesn't really affect the resistance in our equation. So length actually doesn't matter in this equation. Now let's talk about velocity. Velocity is defined as the flow rate divided by the cross-sectional area of that vessel. So if you take a look at the next two images, so we have point X and point Y, X having a 1 centimeter squared area and Y has a 12 centimeter squared area, and we have a flow rate of 12. Now, if we divide the flow rate into the area of that vessel, we will have the velocity of 12 centimeter per minute at point X, but only 1 centimeter per minute at point Y. Therefore, vessels with a smaller cross-sectional area will have a higher velocity than a vessel with greater cross-sectional area. The smaller the cross-sectional area, the faster the velocity of flow. So if we apply this to the circulatory system, since we have established earlier that the capillaries has the greatest cross-sectional area, so greatest cross-sectional area, and velocity is inversely proportional to the cross-sectional area. Therefore, velocity is lowest at the capillaries compared to the other segments. When an artery branches, it increases in cross-sectional area. Cross-sectional area is high in capillaries and low in the aorta. Velocity is low in the capillaries and high in the aorta. The low velocity in the capillaries is actually advantageous. It will facilitate optimum exchange of nutrients and oxygen. Let's talk about laminar versus turbulent flow. Laminar flow looks something like this. So it is parallel to the vessel and it flows in layers. The highest velocity is found in the center. In contrast, we have what we call the turbulent flow, wherein the flow is non-layered, so it is disorganized, and this disorganization will create murmurs, bruits, and turbulent flow produces more resistance. Thrombi are more likely to develop if our blood flow exists in a turbulent flow. So how can we predict if a blood flow is laminar or a turbulent one? We usually use the Reynolds number. If the Reynolds number is more than 2000, turbulent flow is expected. And if it's less than 2000, laminar flow is expected. So this is the equation. And Reynolds number is directly proportional to the diameter, velocity, density of fluid, and it is inversely proportional to the viscosity of the fluid. So in this figure, a more than 2000 Reynolds number, you will expect turbulence, but if it's less than 2000, you will expect laminar flow. So we will apply this Reynolds number to the different segments of our circulatory system. Let's start first with the aorta. Aorta has the most turbulent flow because it has a bigger diameter, a bigger velocity, and we know that density and viscosity are more or less the same. Factors which promote turbulence vessel branching, narrow orifice like severe stenosis in our blood vessels, rough surfaces. And this figure on the right, we'll see why the aorta has a turbulent flow. First, it has branching. Second, it has a bend over here from the ascending to the descending aorta. This bend or the curvature will promote disturbed flow from the laminar flow. This figure will show branching, and there will be surfaces wherein the blood will actually tumble, but some blood will go laminar. This one is a flow through a stenosis. This is the normal laminar. Then when it encounters some bottleneck, then flow will actually be disturbed and it can result into a turbulent flow. Let's talk about series versus parallel circuits. So this is basic resistance diagrams from high school. So we have series circuits and parallel circuits. So in series, we see that the current will flow to this line and it will meet all the resistance, and the resistance will add up. So the current that will go back to the circuit will be lesser. But in parallel, the current will be met independently by each resistance. Therefore, the current that goes back into the circuit will be additive. It's like this one. And these are the Ohm's law. So if we apply this to our blood vessels, blood vessel A represents a series circuit and blood vessel B represents a parallel circuit. So the blood flow in A, it will meet resistance 1 and resistance 2, and resistance 1 and resistance 2 will be additive in such a way that the flow that is going out from here has diminished depending on the two resistance. However, in B, since it branched into different branches, the blood flow that goes out here will be the sum of all the blood flows that comes out from the blood vessel which met resistance 1 and another blood vessel that met resistance 2, resistance 3, and resistance 4. Just like this one. So we can apply this to our circulatory system. It looks like a parallel circuit. Here, parallel. However, from here to here, it is a series. So actually, it is a series of a series circuit in a parallel circuit. So the systemic circulation works like a parallel circuit. That is, the pressure is the same in every branch, and each branch receives a fraction of the blood flow, that is a current in Ohm's law, and total resistance is less than the resistance of any of the individual arteries. It's like this one. The individual organs, however, works like a series circuit, like this one, series. Blood flow is the same in every branch, and as blood flows to the series of blood vessels, the pressure decreases, and total resistance is more than the resistance of any of the individual arteries. Again, the systemic circulation looks like a parallel circuit, and the individual organs from the artery to the vein looks like a series circuit. Let's talk about vessel compliance. So compliance is defined as how easily a vessel is stretched. If we have to put it on an equation, compliance is the change of volume over the change of pressure in a vessel. So if we take a look at this figure, if we put fluid into, let's say, a balloon and it stretched, it is said to be compliant. So if it's easily stretched, it is very compliant. But if the vessel is not easily stretched, then it is non-compliant. Then there is another term, it is elasticity. Elasticity is how a vessel bounces back from a stretch. If you take a look at this image, let's say this is a balloon and we put some additional fluid into it. The manner that it stretches will tell us its compliance, and the manner that it stretches back, it tells us its elasticity. The ability to be stretched is compliance, and the ability to bounce back is elasticity. So it's more or less the opposite end of each other. So therefore, highly elastic vessels have a lower compliance, and low elastic vessels have a higher compliance. Let's take a look at the different compliance and elasticity in every segment of the circulatory system. So elasticity is mainly determined by the elastic tissue of that vessel. So the aorta has really a high amount of elastic tissue. Then the artery, somewhat higher. Then it goes down until the capillary, which almost has no elastic tissue. And it somewhat goes up again. So in this diagram, we'll know that the aorta has the highest elasticity, which means it bounces back whenever we put additional fluid, compared to the arteriole or the capillary. Again, compliance is how easily a vessel is stretched, and elasticity is how it bounces back from a stretch. So we can see here an image. This is the arterial end, and this is the venous end. We can see at this end that it has more muscles, and therefore has a greater ability for elasticity than this one, which has a thinner muscle. So this is more elastic than this one, but this is more compliant than this one, because more or less they are opposite. More compliance means it can hold more blood because it is being stretched, right? So in this chart, you can see here that the veins has relatively more volume of blood than the artery. Let's talk about wall tension. Laplace's law tells us that tension is proportional to pressure and radius. So the tension of this vessel is proportional to its pressure inside as well as its radius. So tension is proportional to the pressure and radius. So if we have this kind of vessel, we have a vessel which has a lower radius and a vessel which has a higher radius. So we can safely say that the segment of this vessel, the segment B, has a higher tension than the segment A because of this equation. So the more, and if you're talking about blood vessels, the problem is this segment will soon burst because of the increase of tension. Therefore, this segment should be what we call a weak spot. A weak spot may develop over time and it will expand. And this is the reason that vessels sometimes form aneurysms, like abdominal aneurysms, cerebral aneurysms, and the like. To further explain this one, let's see, we have a cylindrical balloon. This segment of the balloon has a higher wall tension than this one, which has a low wall tension. And this shows the development of aneurysms in our aorta, the thoracic aneurysms, and the abdominal aneurysms. And that concludes my lecture. Thank you very much.